Pharmaceutical contract manufacturers generate vast quantities of data daily. A single run produces continuous streams of material consumption, quality metrics, and labor logs. Yet, when leadership attempts to build forecasting or capacity optimization models, those projects frequently collapse. The cause of these failures lies in a common misunderstanding of how the data is structured. Engineers and financial analysts often export SAP tables and treat them as flat ledgers. SAP is not a flat ledger. It is a highly normalized, deeply complex relational architecture. When you treat relational architecture like a spreadsheet, the symptoms appear quickly. Analysts execute incorrect join logic, artificially inflating material costs, and they ignore operational timing, mapping thousands of labor hours to the wrong financial periods. To build reliable analytics, we have to rebuild the SAP manufacturing data model from first principles. We will trace the exact path of a product from its initial static blueprints through the physical execution on the factory floor, and finally into the Python-driven variance analytics used to measure its financial performance. Mastering this underlying architecture is the mandatory first step to extracting actual operational and financial intelligence. You cannot optimize EBITDA until you understand the exact mathematical relationship between your materials, your machines, and your labor. Every manufacturing process begins with static blueprints. Before a single machine is turned on, SAP requires two planned architectures, one defining the materials and one defining the capacity. This table shows the Bill of Materials, or BOM. It is the exact quantitative definition of every physical input required to make a product, mapping the parent SKU to its specific APIs, excipients, and packaging components. The precision of this table dictates your financial reality. Standard product costing and inventory purchasing forecasts rely entirely on the mathematical accuracy of the BOM. Looking beside the materials, we see a second structure appearing, the routing table. The routing defines the exact operational sequence required to transform the BOM components into a finished product, complete with standard hours. Notice how the work center column expands here. A work center represents the actual physical resource on the factory floor, where the routing step takes place. While the BOM tracks what you consume, the routing tracks how you consume it. Routing data is the strict mathematical basis for all capacity scheduling and factory bottleneck modeling. However, at this stage, both tables are purely theoretical. They describe what should happen, but they do not represent any physical action until a specific order is placed. If either of these blueprints contains errors, every downstream forecasting and scheduling model will inherit those errors. To activate those theoretical blueprints, SAP uses a transactional key known as the production order. This acts as the gravitational center of the entire manufacturing ecosystem. This new central node is the production order. By using the SKU as the join key, it physically binds the theoretical BOM and routing to a concrete calendar timeline. Looking closer, we see the order establishing baselines. It records the planned start and finish dates and establishes the crucial metric of planned quantity versus actual quantity produced. Every order follows a strict life cycle. It begins as a planned order, progresses to physical issuing of materials, and concludes with a financial posting. Many analysts attempt to link material consumption directly to labor hours. That flat file approach fails. The correct relational logic requires using the production order as the intermediary key to link materials to labor. This centralized structure connects factory operations, warehouse inventory, and corporate accounting into a single, highly traceable entity. The production order provides the necessary relational hinge that makes operational analytics mathematically possible. Physical manufacturing rarely matches the theoretical blueprints perfectly. Machines break down, raw materials yield less than expected, and labor takes longer than planned. To capture this physical reality, SAP relies on a process called confirmations. A confirmation is the operational logging of actual floor activity measured against the planned routing. This new confirmations table logs the exact deviations. For a given production order ID, it records the actual runtime hours, the required setup time, machinery downtime, and the final yield. While confirmations track time and labor, SAP uses material movements as the parallel mechanism to track physical inventory flow against the planned BOM. Every inventory action requires a specific movement type code. A movement type 261 records material being consumed by the production line, while a movement type 101 records the finished goods successfully entering the warehouse. Tracking these specific movement types is required to calculate working capital effectively and to measure material inventory variance. Operational environments frequently introduce data errors at this stage. Operators may delay entering their confirmations into SAP, or they might track labor manually on separate spreadsheets. Accurate, timely confirmation and movement data represents the objective ground truth of factory performance. It is the sole driver for reliable bottleneck identification and labor analytics. All of this operational data eventually flows into manufacturing costing. SAP calculates the standard cost of a product by combining the BOM materials, the routing labor hours, and applied overhead rates. At the end of every financial period, SAP executes the variance settlement. This is the financial reckoning for the factory. Variances are generated exactly when the execution data, the confirmations and movements, deviates mathematically from the static BOM in routing blueprints. This formula visualizes how a labor efficiency variance is calculated. It takes the actual hours reported in the confirmations table, subtracts the standard hours allocated in the routing table, and multiplies the difference by the standard financial rate. This same logic applies across the operation, calculating material usage variances when physical yield is low and absorption variances when machines sit idle. Dirty data will aggressively corrupt this settlement. A duplicate production order or an invalid work center entry will instantly distort the variance math, leading to false financial reporting. The variance settlement serves as a precise bridge. It translates physical operational instability directly into quantifiable EBITDA loss. The raw SAP relational model is highly accurate for executing transactions, but its deeply normalized structure is too complex for direct visualization in executive dashboards. Python's Pandas library serves as an automation layer. It extracts disparate operational tables and merges them on specific join keys into a unified dataset. This dataset then reorganizes into a strict star schema. Notice the central fact tables linking outward to surrounding dimension tables. This structural division serves a clear purpose. Fact tables hold the quantitative events, like runtime and variance costs. Dimension tables hold the descriptive context, like the specific SKUs, work centers, and calendar dates. The underlying architecture determines the success of the analytics. A properly engineered data model matters far more than the visual design of the final dashboard. With this architecture in place, leadership can query the system to determine true SKU-level profitability, forecast long-term machine capacity, and pinpoint exact operational bottlenecks. As product lines expand and manufacturing complexity scales, rigorous SAP data modeling is the primary defense against operational blindness. It establishes the reliable intelligence required to drive long-term factory performance.